All right, welcome back to topic 11.8. This is our resistor capacitor RC circuits daily video one, where we're going to find the equivalent capacitance of capacitors in series and parallel, as well as their individual potential differences and plate charges. My name is Dr. Kelly Miza. I'm from Delaware Valley Regional High School in Frenchtown, New Jersey. Before we begin, let's do a little bit of review. So previously, we talked about resistors in series and parallel. So resistors in series current only had one path to travel. Current was the same for everybody on that path, and more resistance on the path meant more equivalent resistance. Resistors in parallel, on the other hand, current had multiple paths that it could travel. The potential difference was the same that was across all of the resistors, and more paths to travel meant less resistance. And we added up the reciprocals instead to figure out our equivalent resistance. So we're going to start by looking at how does this change when we're dealing with capacitors. So I have a bunch of capacitors in series here. And when we have capacitors in series, that's still true that current only has one path to travel. But if you think about what does it mean for current to travel through a capacitor, we're actually talking about how does the charge redistribute itself across these capacitors. Because current is all forced to go through everybody on this path, everybody on this path is going to end up having the same charge. So if I think about what's actually going on with our capacitors, our little conventional current, which we pretend is plus charges, comes and accumulates on this plate, which then pushes our little plus charges over to the next one, which then pushes them over here, which then pushes them over here, which then pushes them and then pushes them, and so on and so forth. So because of that, we end up with some nice electrically neutral bits in between. So our net charge on all of these is going to be the same for everybody. And as a result, when we have more capacitors on this path, instead of adding to the capacitance like we expected for resistors, it actually decreases our capacitance because we're not able to store as much charge because of all of this in-between balancing that it has to do, which means our equivalent capacitance when we're in series is the one where we add up the reciprocals. So it's the opposite of resistors. Don't get confused. So let's look at an example of how we can put this to work. So I'm going to have my beautiful little circuit. I have 5 capacitors in series here. Because they're in series, my equivalent capacitance, I need to add up their reciprocals and then take the reciprocal again. So all of them have a capacitance of C. So I'm going to add 1 over C 5 times to get 5 over C. When I take my reciprocal of both sides, my equivalent capacitance is C over 5. So this circuit behaves the same way as if there was just one capacitor with a value of C over 5. Neat. So let's look at our entire circuit. So our relationship that we use when we're dealing with capacitance in a circuit situation is Q equals CV. I like to think of this kind of like the capacitor version of Ohm's law because it helps us find our charge and our voltage and our capacitance instead of voltage, current, resistance. Anyway, so Q equals CV. So let's figure out how much total charge are we getting from this situation. So the C, our capacitance of this whole circuit is C over 5. And we are hooked up to the battery, which has a voltage of VB. So we're getting a total of CV over 5. Now, what we can do after that is because capacitors in series all have the same charge and they have the same charge as the whole circuit. Remember, it has to kind of like balance itself out. That means all of these guys have that same CV over 5 charge. So if I want to figure out what their individual voltage is, rearranging that equation, my voltage is charge over capacitance. For these individual dudes, our charge is CV over 5. Our capacitance is C. So those C's cancel out, and each capacitor gets a potential difference of V battery over 5, which kind of makes sense. We have the voltage of the battery, and then we split that voltage across 5 capacitors as we go around our circuit loop. All right, let's look at capacitors in parallel. So capacitors in parallel, when we were talking about resistors, current had multiple paths that it could travel, and that's still true. But the way that translates over into capacitors is that all of these branches, all of these paths can have different charges now. because the current and the charge distribution can split itself amongst those branches. The potential difference across these capacitors is also going to be the same, just like it was with our resistors. So everybody up here in yellow, this entire blob of wire is at the same potential, and this entire blob of wire down here in pink is at the same potential. Alrighty, so in that case, more paths, now we have more places to accumulate charge. So more paths gives us more capacitance. We can store more charge in this circuit, which means our equivalent capacitance is just going to be the sum of those capacitors, which opposite of resistors. So remember, they're flippy flopped. So let's look at a parallel example this time. Okay, so we have a battery with a voltage VB connected in parallel to 3 capacitors. Each of them has a capacitance of C. So since these are in parallel, our equivalent capacitance, we're just going to add them all together. So since I have 3 capacitors with capacitance C, I got CCC, so 3C total. So my equivalent capacitance is 3C. So this circuit behaves the same way as if I had just one capacitor with a capacitance of 3C, which means I can find values from my entire circuit using my handy dandy Q equals C delta V equation. So the charge, the total charge that I'm getting out of this circuit is the capacitance, so 3C times the voltage of the battery. Now that I know the entire charge, I can also go look at my individual capacitors. So in this situation, now our voltage is the thing that was the same across all of our capacitors in parallel. So I can just go straight in there. Their charge, their individual charges, is their individual capacitance C times that shared voltage V battery. The charge on each of these capacitors is CV. And that makes sense. So if our entire battery is supplying 3 CV of charge and it has 3 little places that it can deposit it, all of the same capacitance, they're going to split that charge evenly 3 ways. Okay, let's practice with a more complicated situation. We have capacitors in a series and parallel combination. So we have one capacitor up yonder on the top of our circuit and 2 capacitors in parallel to the right of our circuit. I'm going to highlight my little wire nodes just to make it easier to see who's in parallel and who's not. So these guys over here on the right, these are the ones that are in parallel. Huzzah! So I know that capacitors in parallel, I add their capacitance. So my equivalent capacitance of those 2 capacitors is C plus C, or 2C. So this circuit behaves the same way as if those got smushed together, and now I have just one capacitor there with a value of 2C. Well, now these 2 capacitors, there's nowhere else to go, so they're in series. And when I have capacitors in series, I add their reciprocals. So I have 1 over C from my top capacitor and 1 over 2C from my side capacitor. When I add those together, my 1 over C equivalent is 3 over 2C. And if I flip-flop reciprocate both sides, my equivalent capacitance is 2C over 3. So that means this circuit smushes together one more step, and it behaves the same way as if I had one big capacitor with a capacitance of 2/3 C. Let's look at this circuit in its most simplified version. Our equivalent capacitance is 2 over 3C. We can use our Q equals CV equation in order to figure out how much charge are we pulling out here. Our equivalent capacitance is 2 over 3C. So that's my capacitance. The voltage of this fella here is the voltage of the battery. So sticking those together, the total charge that this capacitor holds is 2CV over 3. Now let's start working our way backwards to answer questions about the individual capacitors. So I can pop those guys back apart into the C and 2C because they're in series. Remember, in series, they have the same charge as the entire circuit. So both of these have that 2CV over 3 charge. So if I rearrange my Q equals CV equation over yonder, the voltage across each of these is going to be Q over C. I'm going to take my Q, my 2CV over 3, over C. My C's are going to cancel out, and I get 2V battery over 3 for this top capacitor. If I do the same thing for the side capacitor, my Q is 2CV over 3 over my capacitance, 1 over 2C. That's going to give me my 2C's are going to cancel out, just V battery over 3. All right, one more step backwards. Because these capacitors are in parallel, they have the same potential difference. They have that same voltage as their combined 2C capacitor did, that VB over 3. So both of these have a voltage of VB over 3. So their individual charge, Q equals CV. So its voltage was V battery over 3. So their individual charges that they store is CV over 3. If we put that all together, this capacitor up here with capacitance C had a charge of 2/3 CV. Its voltage drop was 2/3 V of the battery. Over yonder, these two capacitors had the same voltage drop of VB over 3. And they actually had the same charge as well, since they had that same capacitance of CV over 3. So what should we take away from this? Capacitors in series, your current had one path to travel. And since current is the same for all things on a path, that means the charge is the same for all things on that path. And equivalent capacitance is less than the smallest capacitor. Capacitors in parallel, we have multiple paths that we could travel, which means we have multiple places we can deposit that charge that our capacitors are storing. The potential difference across those capacitors in parallel is going to be the same, and our equivalent capacitance is the sum of all of those capacitors in parallel. In general, more capacitors in series, you're kind of spreading that charge that's limited over more than one capacitor. So you're going to have a lesser equivalent capacitance. Whereas when you have more capacitors in parallel, you're able to put a lot more onto those little plates of your capacitors, which is going to give you more equivalent capacitance. And the equivalent capacitances help you figure out the plate charges and voltages across your individual capacitors by smushing them all together, calculating your values, and then popping them back apart again and thinking about what stays the same for series and parallel combos. And as a reminder, 1 over C equivalent in series is equal to the sum of the reciprocals of the individuals. And if you're in parallel, your equivalent capacitance is just the sum of the capacitors. And that'll do it. Thanks. See you next time.